Okay, neutral weak interactions, and we also call them as the Z boson interactions. Now, since in the last lecture we talk about the current interactions, and I told you at that time that these weak interactions are actually mediated by either, we say that the mediating particle in terms of the weak interactions either W plus minus or Z0. In the last case, we were discussing about the weak interactions that are mediated by W plus minus, and we call those interactions as the current interactions. Now today we are going to talk about or discuss about the neutral current interactions. That is the weak interactions where we have the mediating particle as this Z0 boson, or simply we call this as a Z boson. Now, if you remember in the last time, we see that as the exchange of this W plus minus happens, the flavor is changed. What I mean by the flavor is changed, that means the up quark, we see that the up quark goes down quark, that is this U quark will couple to W plus minus and it will change to the down quark. Similarly, the strange will go to the charm quark, and the top quark will go to the bottom quark with the exchange with coupling of this W plus minus. Right. This is the case when we were discussing of the current interactions. Now, besides that, these weak interactions are also mediated by these Z0 bosons. Okay. So we call them as neutral gauge bosons. Neutral gauge bosons. Neutral gauge boson, or simply we call this as a Z0. Okay. Now this Z0, like we see that in this current interaction, this W plus minus couples to quarks as well as the leptons. Uh, Now the Z0 boson also coupled to quarks as well as the leptons, but it does not change the flavor. What I mean by it does not change the flavor means here up quark goes to down quark. So once it couples with the W plus minus, it up will change its flavor to go to the down quark. Similarly, the strange will go to charm and so on. But the Z0 in this case in Z0 boson, this will couple to the both quarks as well as the leptons, but the flavor is not changed. So let me represent it by some diagram. So here, if this is F stands for some quark or a lepton or simply some fermion, because quarks and leptons are fermions. So the same this fermion goes out which comes in. Yani it does not change the flavor once it interacts with. So there is a no change in flavor in case of this Z0 exchange, no change of flavor. Whereas we see in the previous case, the flavors are being changed while we are talking about the quarks or the leptons. So if we look at this particular interaction, since the flavor does not change, so we can say that this interaction is very much similar to that of the photons, because we know that when some particle will this interact with a photon, when the mediating particle, like in electromagnetic case, the particle remains unlike, for example, the scattering of an electron. The electron comes, electron goes, and there is an exchange of it couples with a photon, because the photon is this mediating quarter in case of the electromagnetic interaction. Then what makes this Z0 different from that photon exchange? Okay, so there are actually two important properties which make it different from that photon interaction. The first one is that this Z0 jo hai, it couples to the neutrinos. This Z0 couples to neutrinos, and you know that neutrinos are massless particles, neutrinos, whereas the photons do not. So that is the main difference. Photons do not, right? Because the neutrinos also have zero electric charge, they are electrically neutral, and this is one distinction. The other is that the Z jo hai, Z has a mass of I told you last time also, around 92 GeV. The approximate weight is 91.1 GeV per c square. So that is why. So this is the reason that these interactions are short range. Weak interactions are short range. So the interactions are short range because of the mass of this mediating particle, short range. Okay, try to understand it. in a very simple way, I say that the weak interactions are mediated by two particles mediating quanta. One is W plus minus, where the interactions via the mediating quanta is W plus minus. We call them as a current interaction, and those weak interactions where the mediating quanta is your Z boson, Z gauge neutral gauge boson. We call those interactions are neutral weak interactions or Z boson interactions. Right now, in the previous case, we see that the flavor of the quarks changes once it couples with W plus minus, like these cases. Whereas in case of this Z boson interaction, the flavor does not change. Yani the same particle comes out, which comes goes out, which comes in. There is no change in the flavor when there is an when this fermion or some quark or a lepton couples with Z0. So these interactions, we can say that since the flavor does not change, so we say that they are similar to the photon interaction, some electromagnetic interaction. But what makes it different from that electromagnetic interaction? One thing is that Z0 will couple to neutrinos, whereas the photons do not couple to the neutrinos. And the second is that it has a mass of this, whereas the mass of this photon, it's actually a massless particle, very small mass. Less, almost zero mass. So nevertheless, I will say in any process where there can be a photon exchange, there can also be a Z. So in any process where there is a photon exchange, there can also be a Z0 exchange. What I mean by this, for example, I will consider an electron positron scattering. For example, I consider an for electron positron. This is an antiparticle of an electron scattering into a pair of final state particles, into a pair of final state particles. What actually happens? The electron will annihilate a positron as a result. So they are massive particles, the energy conversion of mass into the energy. So as a result, we will get some energy, and that energy is being released in the form of a photons. So let me make this with the help of this diagram. So I'm making two diagrams where in the one case I will show the photon exchange, and then there is a Z0 exchange. Okay, so let me write it like this. Okay, fine. So as I said, we have some electron and this is some positron. We are representing it outgoing in the Feynman diagram. As a result, we will get two these photons, gamma. So there is actually a photon exchange here. Gamma, we are actually representing it as a photon exchange. Also the same process, I can also represent it by like this. Here we again have the two gammas coming out, and here we have an electron, and this is a positron here, but the mediating quanta here is a Z0, Z boson. Now obviously we know that when there is some exchange process, there is some propagator involved, like we say in the case of the current interaction. Now what is the propagating operator? The propagating operator in case of an electromagnetic this photon exchange, the propagator here, let me write it here, the photon exchange, the photon exchange has a propagator 1 by s. Now what is this s? S is the center of mass, square of the center of mass energy, because center of mass energy we represented it by under root s. So s here will be the square of the center of mass energy. So where s is actually the center of mass energy, center of mass energy. We have discussed what I mean by the center of mass energy. Whereas the Z exchange has a propagator of this particular, this is for this particular case, and for this particular case where we have a Z exchange, the Z exchange has a propagator. It's given by 1 by S minus mz square C4, mz square C4. Okay, this is the propagator in this case, and in the case of a photon exchange, we simply have an photon exchange, this propagator of 1 by s, that is the center of mass energy. Now I am discussing here two different cases. Now for relatively low center of mass energy, that means where this under root s is very less, So for less center of mass energies, what will happen? This center of mass energy, what I mean by less, that means this center of mass energy root of S should be very much less than this mz c square, yani the mass of the Z0 boson. So it's like that means, for example, we know that the mz c square is around your 91 or 92 GeV. So that means the center of mass energy is very less. It will be around some 1 GeV or 2 GeV. So if I talk about the 1 GeV or 2 GeV, that will be considered as a less as compared to the rest mass of the Z boson. So in that particular case, this Z exchange process contributes least. So Z exchange process जो है, it will contribute least. What I mean, so if it contributes least, it can be neglected. It can be neglected. Let me go to the next page. Okay, so this can be Z exchange process contributes least and can be neglected. However, as this S grows, however, as this under root S grows. Under root S grows means when the center of mass energy is very high. So grows such that it will become comparable or greater than this mz c square. Yani this under root of S will become comparable or greater than this mz c square. Yani rest mass of this Z boson. Both these diagrams are equally equivalent. Which two diagrams are equally equivalent? Let me write. Let me make the diagram here first. So, like for example, okay, uh, both these diagrams are equally equivalent. That means these two diagrams, this diagram and this diagram. So when this is the case, this equivalent means when the center of mass energy is comparable, or I can say it's greater than the rest mass of the Z0 boson. These diagrams are equally valid. Otherwise, for example, when the center of mass energy is very less, the mzc square can be neglected, and it contributes least and can be neglected. Fine. Okay. Now there is another thing uh, about this Z and photon. So this Z and photon also coupled to both W plus minus. Let me write in here. This Z and photon can also couple to W plus minus. Like how it will couple to W plus minus? Like in the first case, we have, if this is a Z, it will couple to this, like this. And this, if is Z, it will couple to W plus and W minus. So if this is W plus and W minus, what it means, it will couple to this Z boson can go to W plus and W minus. Also, in case of a photon, if I have a photon, then I have a process like this. This is a photon, it will couple to W plus and W minus. Okay, what is the authenticity of these two processes? Actually, these couplings were confirmed experimentally at CERN. So these couplings, this Z couples to W plus and W minus, and this photon coupling to W plus and minus, these couplings were confirmed experimentally at this large electron proton collider, isko bolte hain. These are actually two. One is large electron proton collider, then there is the same another this experimental facility that is called LEP2. The LEP1 is meant for some other processes, but there's another experiment setup which we call as LEP second. So this is an experiment at Geneva, this CERN. So you know why CERN is and what is the properties of this, what are the different things we can do at the CERN, huh? Like we had Large Hadron Collider is there, and so other experiments. We have discussed about it in the last unit. Okay, so these couplings, so this W coupling to W plus and W minus, and photon coupling to W minus and W minus, these actually were confirmed experimentally at this particular experiment, LEP, Large Electron Proton Collider, जिसको हम बोलते हैं, at CERN. वहां पे क्या हुआ? Actually they just collide, accelerate these electrons and positrons to sufficient energies, and you know how the collision actually happens. So they actually made this, यहाँ से एक electron को आया है, यहाँ से एक positron आया है. They allow them to accelerate to sufficiently high energies to so when they will interact, they will produce a W plus and W minus in the final state. So for example, if this is an initial state, in the final state W plus and W minus were being produced in this particular interaction. So they confirmed these couplings with the help of this experiment. How did that experiment? They actually allow the electron and the positron to collide at sufficiently high energies. As a result, in the final state particles via W plus and W minus, these two particles, okay, because they are bosons and they were being observed in the final state. Okay, now from the coupling of this W plus to the electron and neutrino, so I will just represent it by the Feynman diagram. So the Feynman diagram showed the coupling of this W plus to electron and neutrino. So let me just show you how it actually happens. Okay, in the Feynman diagram, this is like this. Okay, so here we have an electron coming in, and this is a positron. Okay, this is because they are coming in the opposite directions. That's why we are actually representing Feynman diagram. This positron, the antiparticle, we always show it with with the outward arrow. Okay, this is some W minus, and this is W plus minus. So this process can be represented. This is a photon here. So we say that this W plus minus will, this electron positron will produce a final state particles. However, this Z and the photon also have coupling to W plus minus. So this is electron and positron will just collide, and they will result in the production of a W plus and W minus. However, as I said, this Z and photon also have the coupling to W plus minus. Both Z as well as the photon, which I was discussing here. Z and the photon also have a coupling to W minus. So let me represent these two diagrams with the help of a Feynman diagram when I will consider this electron and the positron into the consideration. So what is actually happening? So let me represent it with the help of this Feynman diagram. So here uh, we have this as an electron. Let me represent this as an electron, and this here as a positron. So there will be a some photon exchange, and it will result in the production of this. Sorry, I'm going to represent because they are gauge boson. So I'm going to represent it by this, not by the straight lines. Okay, so this is W minus and this is W plus, and as a result we here have a photon. So this अगर आप this ये चीज देखोगे, so ये मैं यहाँ पे आपसे कह रहा था, this photon will couple to W plus, but photon will come out of something. So this photon actually comes out from this electron positron interaction, as electron positron, when they are actually accelerated to sufficient energies. Also, what about this other process जहाँ पे मैं Z का कह रहा था? Similar way, we have this electron coming in, and also we have a positron coming in, electron positron, and as a result there will be a Z0, which will then decay to go to some W minus and W plus, W minus and W plus. Okay, so this is actually happening in these weak interactions. So okay, now I will come to some another point, but I hope up to this point it's clear. I will just repeat the same things again what I said. After this particular step, I said this neutral weak interactions are actually caused by this the exchange of this the Z0 boson. Okay, then I say that these processes are similar to the photon exchange, but there will be certain differences. That is Z0, this will couple to the neutron, whereas the Z and also the Z has a mass of this. Then I consider some electron positron scattering, in which I said that the final pair of particles are being, like for example, अगर हम electron positron की, there will be a Z exchange, which will result in the production of two photons, and also the electron positron, there will be an exchange of similar two processes. Then I say that both these processes have a different propagator. In the first case, where we have the photon exchange, it has a propagator of 1 by s, whereas this has a propagator of 1 by S minus m z. Then I do take different cases when the center of mass energy is very low and when the center of mass energy is very high as compared to the rest mass of the bosons. Then I come to the other point. I say that this W plus minus, this Z0 and this photon and the Z0 will couple also couple to W plus minus, W plus and W minus. And these were actually confirmed experimentally by at this particular experiment, wherein the people actually accelerate this electron and a positron. As a result, when the electron will annihilate this electron will annihilate a positron, it will produce a photon, which then decays to W plus and W minus. There will be the energy will remain conserved in the process. Because they are being accelerated at very sufficient energies. Okay, so these have some masses, some energy is being converted. If this photon have enough energy, that it will be equivalent to the energies of, because the mass here will be taken into as an energy. Similarly, I have this process also from that very experiment, that this electron positron will annihilate. As a result, it will produce the Z0, which Z0 then will decay to a W plus and W minus, right? Now you might think a W plus and W minus is actually having the this उनका तो mass ज्यादा है as compared to 141 और इसका तो mass कम है, but because this Z0 has enough energy, and as a result the energy will be converted into the masses. Energy will remain conserved in all these processes. ओके, तो यहाँ पे जो मकसद बोलने का है कि this Z will couple to W plus minus and also the photon will couple to W plus, यानी Z is converted into photon, W plus and W minus boson, and also we can have Z0. Now this is the Feynman diagram representation of both these processes, where we have the photon exchange and where we have the Z0 exchange. And this was actually pretty theoretical, but later on these findings were confirmed by at that particular experiment. So we have a strong experimental evidence of these processes. Yes, that these processes are really happening. Okay, let me now come to the another point. So you might have known about the electroweak theory. I don't know you know about this or not. Electroweak theory. Electroweak theory is that electroweak theory. In electroweak theory, since you know that we have four fundamental forces, one is strong, then there is weak, then there is electromagnetic, and then there is gravitational. And the people are working on the unification of all these forces. Unification means people are actually trying to see that all these forces are the manifestation of a one single force, जिसको हम grand unification बोलते हैं. Grand unification. Okay, so people have not actually achieved up to that point because the gravitational force is creating some problem. That is some different issue, different topic, that is electroweak theory. But यहाँ पे मुझे कहने का मतलब ये है, since you know that earlier the electricity and the magnetism were considered as a two different forces, but later on with the help of a Maxwell equation we see that this electric and the magnetic, they are actually the manifestations of one single force, that is what we call as an electromagnetic force. This is electric and the magnetic oscillations coupled together. So this actually, now later on so now since the electromagnetic and the weak, so there were the people who actually, so when electromagnetic force and plus the weak force, so we are actually saying that these two forces are actually the manifestations of a one single force, that is what we call as this electroweak force. So it actually contains electromagnetic field as well as the weak force. So this theory was actually proposed by few people, and maybe I don't know whether you know the name of those people or not. One of them is very known to us because he belongs to this region. The region means he was from Pakistan. So there were three people actually. One is Glasgow, another was Weinberg, and then there is Salam. Salam is जिसको हम professor of the Salam भी बोलते हैं. Actually he was from the Pakistan. Right now उसके बाद he was exiled for certain reasons. I am not going to into those details. He was exiled from the Pakistan, then he resided there in Italy. अगर आप आज भी देखो, there is an ICTP, International ITCP, International Theoretical ICTP or ITCP, something like that. International ICTP, International Center for Theoretical Physics, ICTP, International Center for Theoretical Physics. That is a very reputed institute in Italy. Actually, it was he who actually who actually started this ICTP, of the professor of the Salam. Okay, now so यहाँ पे this is actually different things, unification of the forces or grand unification, that is actually a different topic. But here since we were discussing the weak force, so I will just tell you. So this electroweak theory was actually developed by these three people, Glasgow, Weinberg, and Salam. So that gives actually the relation between the weak coupling. they actually, so once they were giving this the electroweak theory, they gave it in terms of some this what we call as a formalism. So you know that when we have like in the previous case I told you GW for the current interaction, and we showed you how this GW depends upon what are the things. So this electroweak theory, they give the relation between the weak coupling, relation between the weak coupling and the magnitude of electric charge E and the mass of Z and W plus minus. So developing this electrowave theory, they obtained the relation between this GW, then we have the magnitude of electric charge E, then the mass of Z and mass of this W plus minus. In terms of all these things, they give this coupling. Okay, so what is that relation? So the relation is like this: charge E is always given by in terms of weak this coupling GW sine of theta W. Okay, this is the relation. So we have this weak coupling constant. Now you will see. So it just weak coupling will involve the mass of Z as well as the mass of W plus minus and sine of theta W. Now theta W, what is theta W here? Theta W is called as, is known as weak mixing angle. Weak mixing angle. Okay, this is known as a weak mixing angle, and this is given by something. We are going to discuss this weak mixing angle in the next lecture, which is the what we call as a Cabibbo theory. So we are going to discuss it in detail there. So here this is gives you actually the relation between the electric charge E, the weak coupling constant Q, and also the masses of the W0 and W plus minus. Okay, there is a very complex mathematics behind this particular this equation, but we are not going to into that detail. So I'm just taking you directly to this particular equation, which will give you the relation between this electric charge E, because as I said, this is an electroweak theory, so it will involve both electromagnetic as well as the weak force. So this charge will come from the electromagnetic part, and a weak, you know that this is V, the GW is the weak coupling constant, and sine theta is some weak mixing angle. Now how this mixing angle is defined as, this weak mixing angle is always given by some cos of theta W is equal to mw by mz. Okay, so this is why these two particles actually are taking their role. One is z0 and w. So we actually define this weak mixing angle, a cosine of the theta w, and it is given by mass of w plus minus and mass of z0. Obviously you know that what is the mass of w, that is some around some 1.4 or something, and this is around some what is it, 144. So 144 or 142 divided by this 91. So obviously there will be some value to this corresponding. We are going to discuss it, that is called Cabibbo angle, जिसको हम बाद में देखेंगे. Okay, so this theta mixing angle is given in terms of a mass of W plus and mass of Z0 boson. Okay, so well, in that case, how we can also represent, now you know that from this very elementary level, from the your elementary classes, you know that sine theta is always given by 1 minus cos square theta, sine square theta, right? Or I can say that the sine theta is under root of 1 minus cos square theta. Okay, so using this particular relation, you can see that this, I will write down this energy in terms of this weak mixing angle. So you can write down this particular equation as this E is given by GW, then under root of, because sine of theta W, it will be 1 minus cos square theta W. So 1 minus cos square theta W, that is MW square by mz square. Okay, so using this, we have the weak coupling constant, we know the mass of W, we have the mass, we can find out the relation between all these things, right? Okay, now at energies very less than mw c square, यानी जहां पे हम okay okay, now at energies very much less than mw c square, yani when we have the energy very much less than mw c square, mw c square is around some 141 GeV. So that means when the energy is very much less than this 141 GeV, the amplitude of this W plus minus exchange, amplitude of this W plus minus exchange process is proportional to what is it? That is the amplitude of W plus minus exchange. That is the probability of this W plus minus exchange. It will be always proportional to, and it will depend upon this GW square divided by 4 pi epsilon naught, 4 pi epsilon naught MW square C4. Okay, so this is the actually amplitude of W plus minus exchange is processed by given. So we know the weak coupling constant. We know this is a constant again here, and this depending upon the mass of this W plus minus. Okay, so we can have this particular relation. Okay, so these are some of the important things you need to know about this neutral weak interaction. Like in the previous case, we discussed about the weak interaction. Okay, so that is it about this neutral weak interactions. Now you just go through the current interaction once again, and then go through this. You can just maybe question. There has been a gap of few days. Pata nahi, you have gone through that particular lecture or not. But if not, go through that lecture once again. Then just follow this thing, and you will see the difference. So the main thing is that actually we are actually interested in this the coupling of W plus minus and the coupling of the W zeros, and we are describing them in terms of the different parameters, like we have the masses and also how they actually are actually being produced. So like we see that in this particular case we can see that we have the electron and the proton are being accelerated to the sufficient energy. As a result, they will produce both photon as well as the Z0, which then decays to W plus minus. Fine. So now, if you have anything to ask regarding this, if you understood it or not, if you have some questions, you are most welcome to ask, clear any doubt regarding this particular topic.